The International Space Station is home to scientific research in many disciplines, which is being conducted by many researchers from academics as well as the business sector. For example, recently, the station crew members worked on a combustion experiment called BAS-M. The BAS part is for burning and suppression of solids, and the M is for Milliken, the international chemical and textile company, which has a clear interest in learning more about why things burn as they do. Recently, my colleague Brandi Dean spoke with Chris Desoiza, the vice president of Milliken Research, and asked him what they hope to learn about combustion and weightlessness that they couldn't learn here on Earth.
That's a great question. I actually had several people here at Milliken ask us, well, why are you interested in doing that? What can you learn? Interestingly enough, things are so different in terms of zero gravity versus non-zero gravity. There are some key aspects of burning that you can't really get unless you're in zero gravity. Things like the air convection effect and air buoyancy. And those two things actually affect some key parameters. One, ultimately, what is the temperature of the flame that's burning? Second, what is the spread rate or the rate at which the fire is moving along the fabric? And then third, it can actually affect the combustion products. So if you can affect those parameters or understand those parameters, you can get some insights into things about the burning process or inhibiting the burn process that you really couldn't get in gravity. And in fact, what's most important probably is we ran the experiments both here on Earth exactly the same as the ones we did in space. And therefore, the delta between the two actually gives us a lot of insights into that. And it's pretty important for us to understand that.
So what made you think to try and do this on the International Space Station then? How did you get set up with that?
That's actually a very interesting story. We have a place here called the Gibbs Cancer Center and Research Institute. And one of the gentlemen that's over that is Dr. Tim Yeatman. And Dr. Yeatman also was the interim chief scientist at CASES several years ago. Dr. Yeatman is a friend of one of the executives at Milliken and always was interested in Milliken, and gave me a call one day and said, hey, I'd love to come tour your place. After touring and us talking, he looked at me and said, I was associated with CASES, and I think this would be something interesting for you to consider. And we spent a day and a half covering a lot of deep science, and it became very clear to us that NASA and CASES were doing a lot more than just rocket research. They understood a lot about things that were very interesting to us. Subsequently, we took our leader of our FR technology area, which FR stands for fire retardancy, and had him go up to the Glenn Research Center. And as the story goes, really, really quickly after that, it became clear that there were some opportunities we could do on the space station that would allow us to get possibly some unique insights that we couldn't get any other way.
Well, so tell us a little bit about the experiment itself. What does BAS-M do?
So one of the things that was important to us was to design an experiment that was extremely repeatable. And what was nice is the ISS had a setup that was used for some other things that actually allowed us to do that. And the whole idea here was, let's set up a set of samples that are all exactly the same in terms of their size, and let's vary the technologies that we use in terms of fire retardancy, the way we apply that fire retardancy, and then on various different types of fabrics. And the objective was, let's run all those experiments on the same equipment here on Earth and get all of our parameters. Let's run all those same experiments on ISS. And the idea there was, it's going to allow us to do a couple things. One, there was a question mark on whether things that could actually burn, if fire retardants would actually cause them to be fire retardant in zero G. So that was one of our things. The other was airflow. Can you do something with airflow that lets you control all of those parameters that deal with things like buoyancy and convection that will allow us to say, get information about things like what causes the propagation, what interrupts burn, does different airflows that are interrupted differently cause different things to burn differently. And one of our key areas for us that is a very, very difficult area is in synthetics. So many people are familiar with 100% cotton, pretty common. But one of the things about fire retardancy is you can't be protected if you don't want to wear the garments. And what we learned was having great performance, great durability wasn't worth it if it wasn't comfortable. And we have a lot of history here at Milliken with how to take synthetic materials and make them have all of the right moisture management properties, all of that. But unfortunately, synthetic materials are very, very difficult to make fire retardant. So one of our key objectives with the experimentation was to vary the synthetic content in a variety of these samples and see if through this controlled process of airflow and also in zero G, we could get some insights on maybe a molecular level on ways in which we could get a breakthrough in synthetics. Because if we could get a breakthrough in synthetics, you could now create probably the most durable product from an FR standpoint anybody's ever seen, and get all those comfort features like you see, all the football players and baseball players and all the runners talk about. It used to be they wore cotton. Today they're wearing highly engineered synthetics because they're very comfortable. And if we can do that with FR, you've now got all the people in the military, industrial worker that want to wear their protective clothing, which is really, really important. And these experiments were one that we thought would give us insights into the synthetics that we couldn't get another way.
So the point here is you've I'm guessing sent some samples of these up to test on. Is that right?
Well, yeah, we sent a lot of samples. They were all about 100 millimeters long and about 25, 30 millimeters wide, and they were all exactly the same. In other words, they all started with an ignition, a control, something that you knew would burn, and it was attached to the material that was supposed to be fire retardant, okay? And what was attached to either had a different technology, was a different fiber or fiber blend, or the application technique was different. So every single one of those was the same. So there was no variation in how those products were put together, which was nice. And we ran those exact same experiments here on Earth as well as there. And it went really well, much greater than we could have hoped for. The preliminary results we got have given us some really surprising information. One I'll tell you about that was just very interesting to all of our scientists. 100% cotton is usually used as a control because it burns really, really well. Now it forms a char, but it burns reasonably fast. So if you were to take a 100 millimeter long sample of 100% cotton and ignite it like we ignited it here on Earth, that sample would burn in several seconds. In space, the big surprise was it burned completely like you would expect, but it took 10 times as long, which really told us that the buoyancy, the airflow, and all that has a very significant controlling factor because the control, which had no FR on it, just took so long to burn. So it gave us some insights into what can you do to affect that here on Earth in a different way. And that when we get into that information a little more, again, it's a little preliminary, we'll figure out whether we need to go run another set of experiments. But right now we got more data than I think we can handle trying to go through it all.
Thanks so much for joining us. And again, this was Chris Desoiza, who is the Vice President of Milliken Research. Thanks again.
Thank you.